Right, so here's the plan of the talk. I'm a philosopher of science, so my main focus here is going to be on epistemological aspects rather than values aspects. I'm going to be focusing in particular on epidemiological models, which have obviously been right front and center during the COVID pandemic. There's a large philosophy of science literature about such idealized models, and I want to bring some of that to bear in the case of COVID epidemiology. The title of the talk is Pandemic, Modeling Good and Bad. Really, the sequence of the talk is Pandemic, Modeling Bad and Good. So I'll be criticizing one kind of model and then going on in a sort of more positive take, praising other models and how it should be done. What I'll begin by doing is doing a bit of a detour into the background philosophy of science, looking at some sort of toy non-epidemiology examples, just to sort of make clear what the conceptual terrain is here. So that's what I'll start with now. So I want you to imagine two possible kind of worlds we might live in. First world, one we look at first, is what we might call a stable world. And so this is a world which should be rather familiar to anyone who's studied any science or indeed philosophy of science. It's a world in which causal relations are stable and long-lasting mechanisms, structures, functional dependencies, they all persist across many cases. In the extreme case, you get laws that are universally true. How best to investigate a world like this, a stable world? Well, the answer is to find out these incredibly useful relations that hold always and everywhere. Find out these cogs and wheels of nature. Find out what the laws are, if you like. And the obvious reason why that's the best way is that knowledge of these cogs and wheels that are stably applying in lots of different contexts is the route to remarkable power we're all familiar with. The route to interventions, predictions, and explanations in terms of these long-lasting laws and causal relations. Also enables you to build technological artifacts where you can shield off things where these relations reliably hold, you get working gizmos. As it were, the image of science here is a familiar one. Beneath this sort of messy imperfection around us, there's an underlying order. And finding this order is science's mission. So my main focus today is going to be methodological. How should we investigate different parts of the world? And if the world is like this, a stable world, I'll give you an example to sort of show a classic method around us to investigate such a world. Here's a sort of textbook, A-level physics example. Suppose we discover suppose there's a moon, newly discovered moon orbiting around a planet. How can we predict the motion of this moon? And the obvious move is to go to a well-established, relevant piece of science, a Newtonian two-body gravitational model. Why does this move work? Because we have good reason to think that the effects of gravity are stable right across the universe. Any new moon you find is going to be the same Newtonian gravity model will apply. All you have to do is just tweak the local parameter values, the local masses and motions, and then the model unfolds like clockwork and tells you what's going to happen. There's a high degree of certainty in our science. You can be very confident we can predict the orbits of these moons. I'm going to christen this the master model strategy. If there's one set of relations that holds widely, if you can find out what these relations are, then this model is going to be incredibly useful. Just plug in and play across many different contexts. And the same is true, even unlike the sort of case of moons orbiting in vacuum in space, the same is true even if there's a noisy environment, like what is typical in social science, all kinds of different factors in play. Nevertheless, if you've got a stable factor, then if your model captures that, you can be confident the model is going to capture at least one of the factors in play, even if there are also other noisy factors complicating things. So that will guarantee us at least we get partial explanations and some guide to interventions. If we tweak this factor that we can be confident is there, then we can be confident it will have a certain impact. Now, the key thing here is what is our epistemic warrant for doing this sort of methods? The warrant is the model must have empirical success. Even if it doesn't predict correctly here and now, it must predict correctly somewhere. Otherwise, you have no reason to believe it, crudely speaking. So if a particular relation holds good in a laboratory experiment, and we're confident that this relation is stable and holds good in many other places, then that laboratory experiment gives us warrant to believe that the same thing is going to be happening over here and over here and over here. And if in any particular noisy case, we want to get accurate prediction, then we have to sort of fill in the extra noisy factors each time, case by case. you have a sort of foundation of these stable relations that are holding everywhere, and then you can fill in the sui generis details as required. And this goes way back almost 200 years. John Stuart Mill was an advocate of this methodology. And the thought is that this is actually better than just trying to accurately predict in each individual case. Individually accurate prediction requires taking into account the local one-off factors. Perhaps science should be more interested in generalizable knowledge. Note, generalizable means stable in my terms. It means relations that we can be confident hold widely across many cases. So that's one kind of world. Now I want to introduce a second kind of world, which I'll call a fragile world. And this is quite the opposite, where you cannot rely on causal or the other relations holding stably across different cases. Rather, they hold only intermittently. They're often fleeting, and the key thing is it's very unpredictable when they will or will not hold. Picturesquely, one might imagine it as being like bubbles winking in and out of the distance in a boiling soup. Gave me the excuse to put this photo on the slide. So in a fragile world, just because something caused something over there, that doesn't mean it will still cause something over here. It's not like gravity where you can rely on it behaving in much the same way across different contexts. Now there's much more widespread uncertainty, and scientific life is clearly much more difficult. You can't just find the master model that will apply everywhere. Rather, you're going to have to get stuck into the contextual details each time. There's a scheduled scan, that's good to know. I wouldn't want a virus on Kings's computers, which is a major factor in my well-being, whether that's the case. So if you have a fragile world, now I've lost the, Evelina, now I've lost the responsiveness on, and now we're back. Good. Even I can learn how to use these things a bit. So let me give you another toy example to show how you might investigate matters if we're now in a fragile world rather than a stable one. So we're going to have a moon again, but this time a toy moon. Imagine it's a toy moon. The child is running around, perhaps orbiting around a toy planet, small child in their playroom at home. Suppose you want to predict what's going to happen to this toy moon. Will it carry on being carried by the child around this toy planet? So is that analogy to the real moons in the skies? But now, of course, in this new context, where the moon's motion is controlled by the child, it's much more uncertain. Sometimes the child will carry on carrying the moon around the toy planet. Sometimes they won't. They might get distracted, interrupted, or bored. Perhaps it's some remote online lesson because it's during a pandemic and the teacher says only do it 2 times and then do something else, so they stop. Or perhaps there's a friend there, they want to give the friend a go. It's 100 different reasons which potentially might disrupt this circulation of the toy moon around the toy planet. In other words, we no longer have a stable situation. The child continuing to circulate the toy moon around the toy planet happens sometimes, but not all the times. It's not like gravity where we've got a universal thing, rather it's a sort of messy, unreliable thing. So how do we tackle such a case? Well, of course, informally, perhaps there are many different models of the child's behavior. One is just that they'll carry on doing it because they seem to be enjoying it, but there are many others which are potentially relevant. What will the child do if they have friends present? If they're in a context of a school classroom, they might behave differently again. If they're tired or bored, if they've got a brother or sister with them who they lost, and they're going to do is hand over a moon to that bastard. I have 2 older brothers, still bitter all these decades later. Or the background context, perhaps the child's affected by poverty in the family, or the parents are newly divorced, or they've moved into a new house they're not settled in yet. 100 possible different things. The point is to predict what's going to happen to the moon, and then to explain after the fact why what happened did happen. We need to investigate these contextual details, as it were, which of these models of the child's psychology in this case is the one that actually applies. Dogmatic adherence to any one model will inevitably lead us astray, because none of these models apply always and everywhere. They always apply only sometimes. This is a fragile world kind of context. So the point is, in order to predict and explain, lots of extra local work is needed. A bit like I was saying earlier in Catherine's talk, there's a sort of menu of possibilities of these models, a menu of things that might apply, It's good to have a menu. This can sort of give us clues of what might be going on, but that's never enough. You need a whole lot of extra local contextual investigation. Other things beyond the models we mentioned on the previous slide, things like what is the character of this child? Is the child generally frustrated or angry about something? Even something like, is the weather bright or is it miserable? These are all little contextual cues and triggers you've got to take into account if you want to predict and then to explain the child's behavior. And of course, it's exactly these things that the parent or other carer will actually consider when they're analyzing the behavior of a child, interpreting the behavior, trying to understand what interventions will be effective. Okay, so stepping back a bit, what's the picture here? In a fragile world, as we were saying, the master model methodology, as I call it, is going to be less useful. The Newtonian gravity exemplar is a great exemplar. You've got stable relations. Find the model that captures the stable relations and run with it. But it's a terrible exemplar if you've got fragility. That's exactly what you don't want to do. It's something like the toy moon example. You don't want to just stick to one example and think this is my magic bullet, which will predict and explain everything. Instead, you need a different methodology, what I'll label this or contextual methodology. And that's characterized by exactly what we were just saying. A shift towards contextual sifting, a bit like the kind of methods that historians use, a great emphasis on the sui generis local, perhaps one-off lay of the land, lay of the causal land, if you like, rather than just sort of, as Nancy Cartwright put it, rather than just having a vending machine model of taking a model out of your textbook and then applying it without sort of any sensitivity to the local context of application. In philosophy jargon, it's a sort of ideographic, not nomethetic perspective, contextual rather than general law-like perspective. You have a toolbox of mini models. Each time you've got to work out which of these models might apply, and much else is required as well. Okay, so now let's pivot back to the case of the COVID pandemic. The obvious question next is epidemiology. Is that world fragile or stable? And the question is too simple. Any domain is a mixture of fragility and stability, but often for many of the things we care about, it's going to be a fragile world, as it will, as we'll see. And what I'll do the rest of this talk is look at two examples of epidemiological modeling of the COVID pandemic. The one I'm going to attack is, I think, a mistaken application of the master model approach. And then the one I'll praise is a correct application of the contextual approach. Forgive me a moment, a bit of self-advertisement. This sort of general philosophy science perspective. It's a book coming out from me in the next year or so, I hope, called Science for a Fragile World. This epidemiology is just one example of an application of this general philosophy of science perspective. Okay, so let's move on to these examples of pandemic modeling. Here's the first one. It's a very well-known paper, which everyone here would have heard of. It's a paper from March 2020, right at the start of the pandemic, by Neil Ferguson and colleagues at Imperial College, which was responsible for persuading the UK government to impose a national lockdown. I'm about to be critical of this model, so I just want to add a disclaimer. But firstly, this is a very intricate, detailed model. It's produced at great speed at a time of national crisis. And so I think it's sincerely and well-intentioned attempt to inform public policy. So that was noble. Secondly, the authors of this paper, the paper I'm going to praise in a few minutes, has many of the same authors, including Neil Ferguson. So this is not an ad hominem attack in any way. Nevertheless, the point I want to say is that I think there's a big difference in the epistemic status of the two different papers I'm going to look at. And I definitely do not think this difference is sufficiently recognized by the authors. So there is a sort of critical point in that sense. Okay, so as many of you know, the Ferguson model, as I'll call it in this talk, although it has like sort of 20 co-authors, the Ferguson model, there's several dire projections that with no policy intervention, there would be over 500,000 deaths in the UK. And its main policy point was to favor so-called suppression rather than mitigation policy. In other words, put in lockdowns rather than trying to just manage and flatten the curve. They thought trying to manage and flatten the curve would lead to an unacceptably huge number of COVID deaths. And acceptance of this recommendation was the main real-world impact of the model. Okay, so the Ferguson model is originally a model of influenza epidemics. It's adapted to the COVID case. It's a sort of hybrid of in the jargon, compartmental and agent-based models. There's a huge amount of detailed structure of causal interactions in the population, and some of the factors mentioned on the slide. And then it adds in some COVID-specific values to this sort of existing infrastructure of the model, if you like, about the COVID virus's incubation period, reproduction number, and fatality rate in particular. And then using this model, it ran simulations and gave the recommendations that we just mentioned. Okay, so that's the Ferguson model. Now comes the criticisms of it. The main criticism is a very basic one, if you like, and that's lack of empirical confirmation. Do we have the evidence or the data to believe this model is really capturing what's going on? And essentially, I argue, no, we don't. And particularly when you take into account that there are many rival models, the Centers for Disease Control in USA, for example, tracking over 20 different COVID prediction models. Do we have reason to think that this model is better than all those others? Even less so, in my opinion. There's no track record of successful empirical predictions, either in this pandemic or to import from elsewhere, even assuming that it would be legitimate to import from elsewhere. The model mainly deals in projections rather than predictions, in the sense it makes conditional predictions what would happen with these particular policy interventions. Nevertheless, that makes it indirectly testable. And there's a bit of a literature on exactly how good its projections and predictions are. But in my opinion, I'm happy to go over this in more detail in the Q&A. The picture is largely negative. There's all kinds of incorrect predictions, sometimes dramatically incorrect ones. I list some of the things incorrectly predicted in the slide. And as mentioned, there's no empirical superiority for sure over the many rival models. In fact, generally prediction, as many of you will have seen, has been very unreliable throughout the COVID pandemic. Just this last month, case numbers in Britain been going up and down in a way very badly predicted. If you asked me what would be the total number of daily positive tests in the UK 1 month from now, in my opinion, we have very little idea whatsoever. Whether that's going to be going up or down compared to what they are today is little better than trying to predict whether it's going to rain 30 days from now. We just don't know, roughly speaking. Prediction in epidemiology generally is very difficult for good reasons. So this is not an attack on the failure, if you like. It's more to note that the consequences, epistemic consequences of this failure, means we should have dramatically reduced confidence in the model. Now then, even with the sort of lack of empirical success, there are sort of some get-outs that give us some epistemic confidence in a model. For example, it may be that the model's assumptions are so sort of plausible a priori that empirical confirmation may not be totally required to give us some confidence in it. I don't think that's the case here. If you look in the detail, there are many inaccurate assumptions in the models. There are hundreds of different parameters that have to be estimated. Inevitably, some of the estimates were more accurate than others, as it turned out. There's no way that this sort of a priori compelling. Now, the fact that a model's assumptions are inaccurate is not necessarily fatal. There's a large philosophy of science literature on this. Essentially, you can save yourself the model, even if there's lots of inaccurate assumptions, if it's predictively accurate, if it licenses interventions that actually work. But we've just seen that empirical confirmation is exactly what's missing in this case. So we're in bad shape epistemologically here. A further major problem, and again, I'll be happy to talk more about this in the Q&A, is the many factors omitted by the model, which further shakes or should further shake our confidence in whether the model's really captured all that's going on. Now, these various faults, I mentioned they could be excused by accurate predictions. Another way to excuse them, perhaps, is by running sensitivity analysis. Do the results, the projections of the model, depend on getting exactly right scores for the parameters? Do we have some leeway? If they're roughly right, is that enough? The model does have some rather minimal sensitivity analyses, but way insufficient. As I mentioned, there are hundreds of parameters here. It's doubtful it's even feasible to run a full sensitivity analysis, I would say. Never mind all the factors that are omitted. Of course, there's no sensitivity analysis on how important those omissions were. So all in all, I have a rather sort of strongly negative view here. I don't think we have any reason whatsoever to have faith that this model captures the true causal relations that are out there. Certainly not enough to give us well-warranted explanations or well-warranted predictions. And again, the predictive record of both this and other models does sort of little to revise our confidence in a more optimistic direction. So that's the negative part of the story. Now, the interesting aspect philosophically, I think, is to say why this failure, if it is a failure. I think that the model is incorrectly sort of pursuing a master model paradigm, as it were, sort of following the Newtonian gravity model rather than the fragile world model. Each application of this model to a new pandemic is just a matter of tweaking parameter values, just like a new moon system would be a matter of tweaking the values for the mass and motion of the moon. But I think this is fundamentally a mistaken way to model fragile exponenda like a pandemic. Key causal relations, not just the parameter values, but the actual nature of the relations themselves are fragile. They vary greatly from pandemic to pandemic. Even within the COVID pandemic, they vary greatly from country to country, different parts of countries, and different phases of the pandemic. There's huge variability, a bit like with the vaccine interventions that Catherine was talking about. Contextual detail makes a large difference. I'll list some of the things in the slide which vary greatly in this way. You need to know the local history, the local politics, to get a good understanding of what's going to work. Knowledge from beyond the model is needed. So here's a way to sort of picture the contrast between the stability-appropriate methodology and fragility-appropriate methodology. Going back to the Newtonian gravity model, the moon's position and velocity vary continuously. The key thing is the model tells us how they're going to vary. It successfully predicts how they're going to vary. There's no surprise variation that requires knowledge from beyond the model to predict. In the pandemic case, quite the opposite. It would be as if, in the pandemic case, it would be as if the inverse square law of gravity itself varies unpredictably. Sometimes it might be inverse Q, sometimes a straight inverse. The gravitational constant is varying all the time with different moon systems. It's unpredictable, and gravity will even apply at all. Perhaps there'll be no gravity sometimes. And sometimes there'll be significant non-gravitational influences coming and influencing the moon's motion. Now, if you're in a crazy universe like that, it'd be obvious that just religiously sticking to your Newtonian gravity model would not be an appropriate way to predict and explain the moon's motion. You need to take into account all these complicating factors. But this crazy world, as it were, is exactly the world we're in the case of the pandemic, in the fragile world, in my terminology. So the master model strategy is meant to be efficient, and in the world of stability, it is efficient. Once you've got the correct model of these stable relations, it gives you a wonderful shortcut to successful predictions and explanations. This efficiency gain no longer exists in the fragile context of the pandemic, because too many of the target causal relations are fragile. Okay, let's shift to a more positive mode now. An example of, I think, better practice, more suitable to the kind of problem that we're studying. And this is another paper, as I mentioned, from the same excellent Center of Excellence at Imperial College, by many of the same authors as the first paper. This paper, as the lead author is Eric Volz. And this paper, again, very influential on public policy, was in December of last year. And it was the first paper to estimate the greater transmissibility of the alpha variant as compared with the original COVID variant. The alpha variant is the one that I caught around about exactly this time, actually in December. So personal interest in this bastard variant. Right. Okay, what's good about this second paper? In outline terms, I'll look in a little more detail in a moment, is much more data-driven. It picks and chooses simple models rather than this hugely elaborate Ferguson model, and it justifies why these models actually apply in this particular case. That's the key thing. And the result, I think, is that its conclusions are therefore much more convincing. It makes a very good case that the alpha variant was about, R number is about 1.4 to 1.7 times that of the original variant in England at the time of this study. As I mentioned, this study is very localized in time and place. It says England and towards the end of 2020. It actually gives 5 different methods to estimate the transmissibility of the alpha one, all of them independent. I'll just mention one of them today. So random population sampling across England yielded the time and location of all kinds of different positive COVID cases, 2,000 of the alpha variant and 50,000 of the previous variants. And if you can sort of map where the alpha variant crops up and when it crops up, you get a sort of map of the spread of the alpha variant, and you see that it's increasing in its prevalence across England at this time. You want to infer the growth difference per generation. I mentioned this 1.4 to 1.7 estimate. They used a simple model of evolution of two different viruses with different R numbers and how the relative prevalence would evolve in this case. And that's only requires two parameters to be estimated. And that's essentially what they did in this part of the Volz paper. And that's where they got their estimate from. So the key thing is this model wisely chosen? Is it genuinely applicable here? And they make a good case that it is. Firstly, this model has a history of empirical success. It successfully predicts and explains previous differential evolutions of different virus variants. As an aside, a history of empirical success is really the best way to refine the model and to make it more likely to be successfully applied in new cases. When will it apply nicely? How can you make the model better applicable? This model captures the dynamics of virus reproduction when there are no complicating social factors. And there's good reason to think that relevant complicating social factors are not present in this case. Social factors do enter indirectly, of course, because they influence the R number. But again, there are good independent estimates of the R numbers valued at this time and place under these social conditions. Good reason to think that during the period of the study, the R number value was relatively constant. The virus's incubation period, the other parameter, is again well known independently. Finally, straightforward sensitivity analysis showed that the results were not unduly hostage to remaining small uncertainties in this estimate. So the bottom line from this slide is that it was very carefully justified why this particular model did apply to this particular case. And that, of course, gives us much more confidence in the results. To do that, there's all kinds of local contextual factors you had to research and get right. This is what's required. Now, similar remarks apply to many other examples of good work during the pandemic. I'm far from negative about the sort of overall scientific effort here, quite the opposite. There are similar studies, for example, on different transmissibilities of other variants. More recently, lots of intricate, good statistical work on the waning of immunity from vaccines and exactly what factors influence that and so forth. Again, what matters in every case is that the choice of the model is carefully empirically justified. That requires not following a naive master model method, but rather what I call the contextual method. Okay, there's one drawback to the contextual approach, and that is the results are not easily generalizable. It's precisely because you've got to sort of do carefully analysis of each individual context that you lack the warrant automatically to extrapolate it to new cases. So we're not in the happy Newtonian world where we know the same model will apply to each new immune system, quite the opposite. So we need to reassess each time, will the transmissibility advantage, for example, of this alpha variant compared to the original variant, will that still be the same? Will it exist at all in other contexts? This is just one particular time and place in England with a particular set of social distancing guidelines. Perhaps with other social distancing guidelines in other countries, which are different in many ways, it will be a different story. In fact, I believe there is some evidence that a transmissibility advantage is somewhat diminished in other contexts. So the result didn't extrapolate easily. What to say? Firstly, as it were, this lack of transmissibility, this lack of extrapolation to new contexts, that's nature's fault, it's not our fault. It's simply a fact that transmissibility advantage of the alpha variant is not constant across all the relevant environments that we're interested in. So it's much better to acknowledge that fact than to pretend somehow that there is a constancy which doesn't exist. Second point is that if you've got a good piece of work in this context here, then that's a solid foundation stone for seeing whether the same model will or will not apply in this new context, what things might be different, how important is it that this or that thing is different. It gives you a solid foundation stone. The underlying point is that if the target relations are fragile, as they are in this case, then our methods have to adapt to that. There's no use pretending that there's stability when there isn't. So I'll broaden out the last few minutes of this talk. Sort of general context of this, the theme of this conference is policy making in a time of crisis and uncertainty. So the first thing I'd say is that there's a continuity between the kind of study I just mentioned, the Volz paper about alpha variant transmissibility, continuity between their methods and more informal methods. If you like, the Volz paper is, if you read it, is still pretty technical and complicated with these sort of mathematical models and statistical analyses. But I think the methodology behind it, the contextual methodology, can be instantiated in less formal ways as well. Historian-like comparisons of different countries' experiences. State one of many examples of a relevant policy measure. How effective are border controls at controlling, preventing transmission of COVID between countries? That's a simple quantitative question. And then how are border controls best implemented? You've got to share experiences and know-how, best practice, how to organize your hotels, how to organize the actual controls at the airport, and what exceptions to make for freight, for airport personnel, for nobody, how long quarantine periods do you need for people coming into the country and so forth. What exactly has happened across the world is that people have learned from each other's experiences, as well as the core issue of how effective are border controls, which again is something very likely to be fragile, to be much more effective in some circumstances than in others, for some purposes than for others. Now, a model here is a sort of grand word, but it can just be sort of very simple causal hypothesis, something like, at the simplest level, border controls reduce transmission between countries. Perhaps more sophisticated, border controls at this stage of the pandemic of a certain kind will reduce the international transmission by X% or something like that. In this sense, everyone is using models. It doesn't have to be a fancy mathematical theory. It can just be any causal hypothesis at all. I want to emphasize, sort of philosophy of social science hat on, that informal methods can certainly be quantitative, firstly, and secondly, highly rigorous. There's an extensive methodology in all kinds of different areas of social science. So informal doesn't mean sloppy. And in fact, quite the contrary. You've got a fragile exponendum. Informal is very often the way you have to go. And it's much better science than a mistaken formal master model approach. Okay, final section of the talk, rather grandiosely titled The Way Forward. So the first step, methodologically speaking, is is your target fragile? Are you analyzing a fragile world or a stable world? In my opinion, this is the biggest methodological divide at all for much actual science. If the target is not fragile, then master model is highly adaptive, as we've seen, can be a very powerful method. And a good example of this, I think, in the context of COVID, is the vaccine trials. The relation there is, causal relation is, if I have this vaccine, how much protection will it give me against infection and developing serious disease and so forth? And it seems, relatively speaking, that this relation is relatively stable, presumably because human physiology is relatively constant across context. And so then methods that are suitable to stability, like running a large randomized trial to estimate the efficacy of the vaccine, is much more appropriate and has had a tremendous positive impact following these methods. I emphasize relatively stable, as many of you know, of course. The exact efficacy of a vaccine is still contextual to some extent, and it depends on exactly which vaccine, exactly which version of the virus and so forth. And as we've seen, there's some waning of effect over time, it seems. So there's a lot of nuance here, but nevertheless, matter of degree, there's sufficient stability, that stability suitable methods are very powerful and worth following. Nevertheless, there are clearly many other aspects of the pandemic, as I've been emphasizing, where I think the picture is much more one of fragility, in particular the efficacy of non-vaccine policy interventions. Is a clear example of that. I should add, even with the vaccines, even if the physiological effects are relatively stable, as Catherine's talk showed, actually implementing a vaccine program and getting popular buy-in is far from stable. You need a lot of contextual knowledge to get people to actually buy in. So my wife is Russian, for example, and vaccine take-up in Russia is still only about 30%. As compared to more like 70% in the UK. So that's an enormous difference. And just doing a vaccine trial for the effectiveness, I'm not going to tell you anything about that difference. It's all these messy, fragile, social and political factors that explain that difference and success of the rollout on that. Okay, so if we're in a fragile world, as I keep hammering home, detailed local investigation is always necessary. The frustration is that we have a lot of uncertainty. Progress can be frustratingly piecemeal because it might only apply in one context, and then you've got to work again to show if it applies in a new context, and it's difficult. However, if that's the reality, that's the reality. We should definitely turn away from any sort of false certainty that we might get from one-size-fits-all master models. If the models are no epistemic value, then it's of no use, no matter how convenient it might seem to implement it. So, final couple of slides. In a crisis, speed matters, of course. As I was hinting at, a master model may be available immediately. You can imagine a crisis of some asteroid in a Hollywood movie coming to attack Earth. Then brilliant, we've got a Newtonian model on hand to immediately sort of help predict what's going to happen. But if the target is fragile, alas, that means contextual work is needed. As I said, this can be a frustration, but it unfortunately is necessary, crisis or not. And the result is that we might often just be very, very uncertain, particularly in the early stage of a crisis, what the best policy is. But if we're uncertain, we need to face that. Let's put one slide in on randomized controlled trials, and there's others have some interest in this. As is well known, they had a distinguished role in the history of medicine, randomized controlled trials, a dramatic improvement on many of the earlier methods that were used for assessing treatments. However, they have some limitations. Firstly, as I say, they tend to be much better suited if the target relation is stable. That's when an RCT is at its best. I gave the example of the vaccine trials. And as many people have pointed out, RCTs, in addition, are very well suited for so-called internal validity, testing whether causal relation holds in a particular sample that was experimented on, but not necessarily for external validity, or the same relation holds in a new population that might be rather different. And of course, the problems with external validity tie in with notions of stability as well. I'll just self-advertise a forthcoming paper, the Dina et al. One, which explains, I think, in more detail how RCTs are one important tool, but should only be one tool in part of an overall research program. Self-advertising because I'm one of the co-authors on the Dina paper. Don't worry, I'll put a reference up in a couple of slides just to make sure none of you miss it. As many people have pointed out, in the context of the COVID crisis, firstly, RCTs take time, so they may not be immediately helpful, and governments often didn't have time, especially right at the beginning of the crisis, so inevitably you're forced to use other methods instead. And secondly, the limitation of RCTs, again, many people pointed out, is they may be very well ill-suited to various policy interventions. You want to know the effect of a lockdown, for example. Well, lockdown is going to be very different in many different countries, have many different effects in different countries. It's going to be fragile in all sorts of ways. Just doing a sort of crude, even if you could, randomized trial of this country does a lockdown, that one doesn't. It's very dubious how much useful information such a crude investigation would actually give us in any case. So, conclusion, when target relations are fragile, that means we need empirical contextual work. We do sort of a menu of different models, and we've got to do hard work each time to see which particular model might apply. It de-emphasizes the sort of Newtonian style one-size-fits-all abstract model development. Final remark, and again, many of you listening will have good knowledge of this. This all has practical import. It's not ivory tower stuff. So in the case of the UK, SAGE, the official advisory body, as most of you all know, I'm sure, scientific advisory body to the government, was arguably at the beginning of the pandemic top-heavy with mathematical modelers and no empirical field scientists at all, arguably. And the result of this, many have argued, is sort of journalists reporting on the actual deliberations at the time in early 2020. The result of this top-heavy composition of SAGE, if you like, was an initial neglect of on-the-ground experience from other countries and on-the-ground input from practitioners at home, an initial veering away from the contextual methodologies I would call it. And this had impact. Arguably, it slowed the provision of personal protective equipment to health workers at the start of the pandemic, and it slowed the setting up of a testing system as well, both of which were highly consequential in the case of the UK, and likely cost many lives. So ultimately, this stuff does matter. There's the references. Thank you all for listening.